Good afternoon everybody and welcome once again to a session on engineering graphics with me Yash Chawla, lecturer in Mechanical Engineering Department at Parul Institute of Engineering and Technology. Since last time, till last time we had discussed introduction as well as loci of points. Today we are going to move on to another topic, that is engineering curves. So engineering curves have a wide application in engineering, be it an arch in construction in civil engineering, be it a spring in mechanical engineering, be it any component of electronics or say any computer engineering component. Everywhere these curves are applicable. For measuring the distance we use curves, on the maps we use curves, for navigation we use curves. So we are going to study what are the classification of engineering curves, what are the different types of engineering curves available, and then we are going to start with conics today and know the construction of an ellipse by different available methods. So we'll first go on to the classification of engineering curves. There are basically 6 type of curves, engineering curves available for us: conics, cycloidal curves, involute, spirals, helix, sine and cosine curves. Each are different from each other and have very different applications, have different ways of constructions. Some methods of constructions are similar but have different parameters, so the end result have different curves. Let's move on. The first is conics. Now conics can be further classified into 5 types of curves. First is triangle. Triangle is basically not a curve. We can say that it has sharp edges, so we cannot name it as a curve, but in engineering drawing we can call it a curve because it has edges. We have a perception that edges, the figures which have edges are not actually curve, but it's a wrong perception. Even a circle has edges, but those edges are not visible because there are infinite number of edges on this circle and infinite number of line segments that form this circle. That's why it is also a curve, and this can also be classified as a curve. Now why this name conics has come up? This name conics has come up because if we take a cone and we cut it by a plane of different orientation, suppose this is a cone that I have and then I'm cutting it with different orientation, say vertical, horizontal, then with an angle, or again with a steep angle, with a slight angle, with parallel angle. So with different types of angles of the plane that I use, the different orientations of the plane that I use, I get different curves that is there on the cone. So the first is triangle, second is circle. This is a triangle denoted by number 1. This is a circle. Then we have an ellipse, then we have parabola, and then we have an hyperbola. Here in conics, apart from triangle, these 4 curves, that is 2, 3, 4 and 5, that is circle, ellipse, parabola and hyperbola, are concerned with eccentricity. We will be discussing what is eccentricity. Here the eccentricity is equal to 0 for a circle. For an ellipse the eccentricity is less than 1. For parabola the eccentricity is equal to 1, and for hyperbola eccentricity is greater than 1. Then we come to cycloidal curves. We have learnt locus. Now this is another application of locus where locus is used for plotting these cycloidal curves. Now there are 3 types of cycloidal curves. One is a cycloid, second is the epicycloid, third is the hypocycloid. So let's know what is a cycloid first. This curve in green shows a cycloid. Now how this particular curve has been formed? This is a circle with a point P. This circle starts, the point P starts from here, and the circle just rolls over this line and the point P rolls along with it. So the path which has been traced by this particular point P results in a cycloidal curve, which is cycloid. Moving on to epicycloid. Instead of this line, if I make this circle with point P rotate on another circle on the exterior side, as shown in figure number 2, this is a circle with point P and it is rotating on the exterior of this circle, then this point traces this red path which will be named as epicycloid. For hypocycloid there is a slight difference from epicycloid. Hypocycloid the curve, that circle, rotates in the interior of this circle rather than on the exterior as compared to epicycloid. So this curve, this circle is rotating on this blue circle and has a point P which traces this red line, which will, this red curve, which will be named as hypocycloid. Moving on to involutes. To understand involute, take a cylinder, take say a simple rod, and then this is a rod, I am wounding a string around it. I am wounding or unwounding a string around it. आप लोग पतंग उड़ाते हैं, फिरकी होती है, फिरकी में क्या होता है, हम लोग जो धागा होता है उसे घुमाते हैं उसके ऊपर या उसको उतारते हैं. तो there are two types of involute curves that are there. One is a circle and another one is a polygon. This just depends on the cross section of the cylinder. If I am there are, आप लोग देखेंगे, I'll take the same example again. पतंग की सीजन में there are दो टाइप की फिरकियाँ आती हैं. एक there is a solid curve, एक सॉलिड सिलेंडर होता है जिसके ऊपर हम लोग डोरी घिसवा के बांध देते हैं, और सेकंड होता है जिसमें कि देर आर डिफरेंट व्हाट आई कैन से रॉड्स, स्टील वाली जो फिरकी आती है, देर आर डिफरेंट रॉड्स इन दैट. नाउ यू कैन इमेजिन इफ आई कट दैट, इफ आई वाउंड द thread over it, then it becomes a hexagon or a pentagon, and that solid thing becomes a circle. So that is the only difference. In the figure, when you can see that this is a curve, that is a circle, and this string is being wound or unwound around it, so it forms an involute curve. For a polygon, I have taken example of a pentagon. 5 pentagons has 5 sides, 1, 2, 3, 4 and 5. So if I am doing the same process as I did here, if I am wounding or unwounding this string, then this polygon pentagon will result into, the string will result into an involute curve for a polygon. The next is spiral curves. Now spiral curves are, we must have, we draw spirals all the time. It is like in Diwali, we have this chakri that rotates. It's something of that sort. So in the figure you can see that there are 3 types of spirals, say 4 types of spiral. The third has been divided into 2 parts. First is the Archimedean spiral, the second is logarithmic spiral, third is semicircular or quarter circle spiral. Now these are different, the base, if you have a different base, the curve, the end spiral will be different. Here in Archimedean curve, this has been illustrated. This is an Archimedean curve which starts at a point and then ends. This is a logarithmic curves, again it looks like a spiral as you can see. And this is a semicircular spiral, that is, this is a semicircle, and then when we go on to extend it, it becomes a semicircular spiral. In this red you can see this is a quarter circle. Quarter circle means dividing the circle into 1/4 part, that is this, you can see this, this red part, which has been again extended to form a quarter circle spiral. Now the construction and in detail discussion of these spirals will be discussed in coming sessions, so we'll not waste time on this because we have more important things to learn in conics today. So then comes helix. This is a very common thing that you encounter in your day-to-day life. You must have seen a spring. Now there are helix are 2 types, cylindrical and conic. The spring that is there in pens, if you have a pen, just open it up and there will be a spring. If you have a touch knot pen, then if you open it, there will be a spring in it. The spring will be like a helix. So that is an example of cylindrical helix. Now imagine that spring has this cross section. Now if I start to decrease the cross section like this, then it will become a conic spiral. Instead of a cylindrical spiral, it will become a conic spiral. So it is very similar, it's just that the base is big and then the upper top part gets smaller and smaller, or you can turn the other way around also, because it's not necessary that the cone has the base only as the base is big. The base can be small also and then it can be extended also, then also it is known as a cone. So then lastly we have most widely used curves in electronics, CS, engineering, in analysis mostly, because most of the processes that are there, the waves that are there, trace this part, that is sine and cosine. It is very important for mathematics, it is very important for electronics, it is very important for mechanical. So all the branch are covered in this, and you can see that this is a sine curve and this is a cosine curve. Sine curve starts from 0, goes up to pi by 2, then pi, then 3 pi by 2, and then 2 pi, where one wavelength is completed. And this is one sine curve, which is in repetition we get a whole wave. So this the distance between these is known as the wavelength, and this is the negative maximum, this is the positive maximum. For a cosine curve, we start, instead of starting from 0 in sine curve, we start from pi by 2. So all the values of sine curves and cosine curves are absolutely opposite to each other. So we'll start from pi by 2, then we'll go to 0, then we go to the negative maximum, then we go to the 0 again, and then we go to the positive maximum again. So this is one wavelength of cosine curve. So let's get down to the main topic of today, that is conics. Now I have kept this figure on this front page for a reason. See, I have cut this cone into different parts, into different pieces. Now you can see that if I am cutting it horizontal, it becomes a circle. If I am cutting it with right angle, then it becomes an ellipse. This particular black part is has a circular cross section. This has an elliptical cross section. This has a parabolic cross section when it is cut parallel to this line, and this has an hyperbolic cross section when there is the angle of cutting is very steep. We'll be discussing it, no problem. You will be able to visualize it in coming slides. It is just for making you understand that what we are going to discuss. So this figure just illustrates that this is a circle, this is an ellipse, this is a parabola, and this is a hyperbola. So visibly you will be able to see the difference on how these curves are created by cutting a cone, and what actually the end result of the curve is, that is how does it look finally. These are also mentioned in this particular slide. Moving on, first the triangle. So most of you will be wondering that how a triangle would be created by cutting a cone. Then just visualize this. Now I have drawn a cone which has an axis of O dash and A dash. Now I have cut it with a plane which is passing through this point, the top notch. I have passed a plane which is absolutely parallel to the axis of the cone, which is passing through the axis of the cone, and has this A1 and A1 dash as the cross section. Now what happens is, if I remove the front part of the curve, I'll be able to see this this dashed line, which will result in something of this sort, this orange part. This is the back angle. This I have kept it, I have not removed it. The front part I have removed, I have just cut it and I have thrown it off. So this results in a triangle. The plane is passed vertically straight through this top notch, that is the vertex of the cone. So it results into a triangle. Able to visualize it? Then I told you we'll be discussing what is eccentricity. So we have discussed triangle. Now the next few things that we are going to discuss is ellipse, then parabola, and then hyperbola. So let's first know what is eccentricity, so that we are able to make out the difference between these three curves on basis of eccentricity also. Now take a look at the formula, where E is equal to distance of a point from focus divided by distance of a point from directrix. Now what is a directrix? That we'll be discussing in the coming slides. Now you can see this line is known as directrix. Now how this line will be defined is that I'll take any point on, first I'll take any point on the ellipse, say M. Now this is the focus of the ellipse. We all know what focus is, that when parallel rays of light are incident on the curve, those gets reflected and pass through the focus. So this is the focus. If I cut this in half, all the parallel lines, all the parallel rays of light that are coming will be reflected to this particular point F. So the distance MF is the distance of this point point M from the focus. The next is, this point M is at some distance from this line, which is the directrix. Now we'll have one ratio. According to this formula, we'll have the ratio as MF upon M dash. This ratio has to be constant for all the points on the curve. Say if the ratio is coming as, say for ellipse it is less than 1, so it is coming as 0.75. So means MF upon M dash is 0.75, that is the value of E. Then for all the points, that is all the points on this red ellipse, if I take another point here N, then again Fn upon n dash on this directrix will again result into 0.75. Similar thing is with parabola. Instead of that, for parabola, for all the points of the parabola, E has to come equal to 1. For this ellipse, it will be E will be always less than 1. If it is on a parabola, then E will always be equal to 1, and for hyperbola, E will always be greater than 1. So now let's see what is circle. The first thing that we know is for a circle, E is equal to 0. That I already told you previously. Now this is the cone. See, you'll be able to better visualize this. This is the cone. There is a plane. This red part is a plane. Now it is exactly parallel to the base circle, and it has been passed. And this circle is this is the cross section of the cone that has been that is left. So we will be able to visualize it better in this line diagram. This is a cone which I am seeing it from the front, and then this A dash is the plane, this red plane. I have visualized it with a single line. I am just seeing it from this end instead of seeing it in isometric view. So I'll remove the top part because I have cut it. So I'll remove this part A dash and O. So it will be, I have named it A1 and A1 dash. This thing that is result, if I view it from the top, it will be something like this, which is the circle, which is A2 and A2 dash, which is the diameter, and this circle, that is the outer circle, is this base circle of the cone. So I have the resultant circle, for which E is equal to 0. For an ellipse, what I have to do is, instead of cutting the plane exactly parallel to the base circle, I will make it at certain angle. As you can see that this is forming a certain angle, you will be able to better visualize it on this orange line diagram, in which A dash is the plane which is passing through the cone, that is O, B and B dash. You can see that you can see that it is making a certain angle with the this is a certain angle which is not too steep. This is the angle that is being made by the base circle, and I have again removed this O, A and A dash, and I have this